Hi, my name is Kaylyn Crawford, and this was Lab 5, Choose Your Own Adventure. So I decided to investigate the motion of a cart down an inclined plane, and the main objectives I wanted to explore here were to model the motion of a cart on an inclined track after it was released from rest relative to known forces. And so I really wanted to see if I could determine the acceleration of the cart during its motion from only observing the motion data, and also from knowing the net forces that were acting on the system. And so the main principle that was used throughout this lab was Newton's second law, which we know to be the relation between the net force and the mass times the acceleration. And so in this lab, I determined that the net force on the system was the x component of the weight force minus the frictional force. And I'll get to how I determined that in a minute. So first off, the central questions I wanted to address throughout the video were, do the models indicate constantly accelerating motion? And if so, how is this portrayed by the graphs? Next, what is the value of the acceleration due to the forces, the x component of the weight force, and the frictional force? Lastly, how would you expect the acceleration due to gravity to be different when friction is and is not considered? And I'll go back to these questions throughout my video. So as a brief introduction to my results, I found that constant acceleration motion did indeed occur, and that changes in the velocity were constant as the cart moved down the ramp. And also I found that non-constant velocity occurred due to constant but non-zero net force. So how I determined the net forces, I first drew a diagram of the real system that I was observing, and it was the cart going down the ramp, which was at an angle theta to the horizontal. And as you can see, the y components of the net forces on this system, which was the cart, are zero because the normal force and the y component of the weight force cancel. So that leaves the x component of the weight force and the frictional force, which is negative because it's in the opposite direction to the cart's motion. So as you can see in yellow, the net force I determined was the x component of that gravitational force minus the frictional force. So now that we have a brief introduction to the model at hand, I can actually show you the video that I analyzed. And as you can see, I set my x-axis parallel to the ramp itself, and I calibrated it to the width of the ramp, and the origin is set where my hand is right before I released it. And I was able to get position and time data points for this system. And as you can see to the right, the positions and times are output. And from this graph alone, I can tell that there's constant velocity, because as you know, the velocity is the time rate of change of the position, which as you see is not constant here because the slopes are changing instantaneously. So to get a better idea of what actually was going on, I wanted to create a computational model to see if the forces that I speculated were acting on my system and the initial parameters that I set could actually give me a prediction of what was actually the motion that was occurring, and if that agreed with the observed motion. So how I used Newton's second law in this computational model, I first used the net force that I had determined, and that equivalent statement is to the right of the VPython code. And I also used another equivalent version of Newton's second law that states that the change in momentum is equal to the net force times the change in time, and I used that in updating the velocity, which as we know, changes in velocity are proportional to changes in the net force, which we know to be constant but non-zero. And so from this average velocity calculations that we're updating, I was able to also update the position as the cart moved along the ramp. And so now to actually run the module, you get a visual of the cart down the ramp, and the yellow block moving down is indicative of the cart, and the green line is the trajectory. The blue arrow is actually the magnitude of the weight force, and the red arrow is just that positive extension of the weight force upward, and it also outputs a graph of what the expected trajectory the position and time of the X data points are for this system. And so to compare those, I inserted the position and time data points for both the observed and predicted motion into Excel. And as you can see, there's very similar trajectories for both the predicted and observed models. And so that led me to want to determine if the velocities were in fact as similar as well. And as you can see, the observed actually doesn't follow as a linear correlation as the predicted, but it does display a linear relation. And so from this, I could tell that there was constant acceleration, because as you know, the acceleration is the time rate of change of velocity, and the derivative of a linear display, as you see here, is a constant value. So even though I didn't know the value of the acceleration yet, I was able to determine from the predicted and observed velocity graphs that I did have constant acceleration with this model. And that makes sense because the forces were constant that were acting on this system. So, in following up, I wanted to compare the acceleration values for the predicted and observed data, and I found that they were quite similar. For the predicted, it was 2.41 meters per second squared, and observed it was 2.77 meters per second squared. And I speculated that disparities between these values could have been in fact because I did not include drag force, and I chose not to include drag force because the model was not moving at such high speed that I thought the magnitude of it would actually affect the calculation for the net force and thus the acceleration. So what? Newton's second law basically proved here that it can be used to accurately predict the acceleration on an object, even at an angle to the horizontal, which we saw here. And that with knowledge of the net interactions of the system and the surroundings, we can predict the acceleration that will be acting on the system, which we did here to quite a good degree because the values did agree quite well. And so going back to one of the central questions, if I had not included frictional force, would the value of the acceleration be higher or less? And so going back to the original determination of the net force, if you see in yellow, if you did not subtract that component of the frictional force, you would actually get a greater value for the gravitational or weight force, and thus your acceleration would end up being a higher value, which makes sense. If you did not have a frictional force in the opposite direction of motion, you would get a greater value for the acceleration because the velocity would be changing at a faster rate because you do not have a force acting opposite in the direction of motion. And so those were the main ideas and important revelations that I came to in this lab, and I hope you enjoyed it. Thank you.